All right, what's up, everybody? Welcome back. Got my afternoon cup of coffee and about to make this video on torsion. And hopefully, by the time this video is over, you will be able to describe the deformation of a circular shaft with an internal torque in it. And then you'll know where the torsion formula comes from, which will be another very important equation that for your introductory course in mechanics and materials. And so we'll start off. Maybe you've all experienced torsion in some way or another. Maybe twisting your back, right? You've done this some. You've created an internal torque in your spinal cord or spinal column so that you can have some muscles that are twisting, right? Or taking a piece of chalk and twisted it till failure and seeing the plane of failure that occurs. But in any case, let's take a look at here a solid circular shaft that's subjected to twisting, or this external torque here, or this, actually, let's make it seem like if I made a cut at this distance L, I would see this internal torque on the inside of that. That would be what's going on the inside. And as always, this double arrow indicates the direction in which your thumb should go, and then the the rest of your fingers will curl around in that direction right there. Okay, so here that's the indicating the direction of the torque. And just to make sure, just in case there are any questions, torque is really just another moment. It's a moment that causes twist. Moment causing a twisting action, causing twist right there. And it's no different than any other moment, except the moments that you've looked at in 2D are about the out of plane axis in 2D. And here in this case, we're talking about a moment about the x-axis, which happens to be running through the centroid of the circular shaft. And so when we apply an external torque, the things you want to know is that the circular cross sections, the circular section. So here, let me see if I can draw a circular section right here. Bam, just using my little, actually have a little tool that I use, or it's actually not, it's not a tool, it's just the inside of a tape. But here, bam, to draw my circular sections right here. These circular sections, when you twist something, circles remain circular. So there's no deformation, remains circular in terms of the cross section. There's no warping out of plane or anything like that. But the thing that does change, the thing that does is that these lines that are longitudinal at the start line. So here, let me draw a longitudinal line that's parallel to all this business. Bam! That these longitudinal lines twist, or they deform. So here, what would happen is if that line right there, if that gray line was my first line, or before at my undeformed, before loading, then I apply a load to it, and I end up with right here some sort of twisting action. So this gray line turns and rotates and twists right there. And as you can imagine, what the actual deformation here, because we have a small deformation assumption, the deformation that we would look at or measure is this angle change right here, that angle change. And as you may have noticed from the strain videos, an angle change is associated with ding, 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 shear strain. Yay! Which means that this torque, internal torque, induces shear stress. Yes, shear stress. And we will write here this gamma. And in fact, this angle right there is a shear strain that's going on. And another thing to note is that if I look at the cross section of this, so if I look at my cross section again, let's start with this gray being my undeformed line right here. Ooh, gotta get that through the middle right there. Okay, and if that gray right there, oh, come on. Okay, that gray line right here, right through the center of my cross section, put that dot back there, let's say that's the middle right there, that deforms to here, this position right here. Bam. And this angle change right here, which why not use green just to let you know that's different than the shear strain. This angle change right here, we'll call that phi. That phi right here is called the angle of twist. And in particular, in this one, this is the angle of twist at L. If this, this is 0 right here along my x-axis. This is my angle of twist at L. And if you can tell from the side view of this line right here, this angle of twist decreases as I get closer and closer to my fixed condition right here. So it's a function of this, function of the length, or where we are along the length of my circular shaft. Using our reasoning of the angle change here, we said that this is associated with shear strain, and by knowing that it's shear strain, we know that this twisting induces a shear stress, and that shear stress is on the surface of the circular shaft here. And so if I look at, let's say again from this line right here, I see, let me draw for ourselves here, let me draw this line all the way across, this blue line, right here, bam, like that right there, okay? And so we notice that we have no deformation right here at the center, and then as we go out, our deformation, the amount of, or distance from the original to the deformed line, if you will, increases, which would tell us that, hey, you know what, since this deformation right here compared to this line versus this line is increasing linearly, I would imagine that the stress also increases linearly, and the fact that's true, okay? And so here, if I have, for instance, where I have the most deformation, I would anticipate on this little, if I could zoom in and I see a little rectangular area on the surface here, this location right here will experience the largest shear stress, okay? This will be my tau max, and this would be some incremental area. So I could say in between here, along the length, or along the radius of this, right here, I have some shear stress, which I will denote as tau, acting on this little square area, which I will call dA right here. And here, if the radius of my shaft here, let's take the radius here, let's say the radius of the shaft, we'll call that, a lot of your books use the symbol C, so we'll say C is the radius of the shaft, right here. Okay, maybe you like to use rho, or R, not rho, but R, right here. And we'll say rho is the distance to some specific location, all right, here we go, rho, right there, bam, that's rho. And I don't even know, but hopefully you can. Okay, zoom in on your monitor or whatever, right? And here you've got this relationship going on. So we know that this stress here, because the deformation, or the deformation going along the radius from here, where it's 0 deformation at the center line, to the outer edge where it's the maximum deformation. We know that's varying linearly, so we have this intuition or feeling that hey, the shear stress along the face here is also probably varying linearly. Okay, so let's take a closer look at this cross section here. And so if I go down, I just redrew it here. If I look down on this right here, if I zoom in, again, just because here at the outer edge is where I experience my largest deformation, I anticipate having here, and I'll use tau for stress, or use red right here, the shear stress on this little incremental area right here, I anticipate it's saying it's at the very outer edge, tau max, right here, at the very outer edge, a distance c from the center here, a radial distance c, I expect the tau max, or maximum shear stress, and I anticipate this all the way around the entire cross section. Okay, on the outer edge is my maximum shear stress, and then here, if I take an arbitrary location or arbitrary radial distance from the center here, I know that I'm going to have some sort of linear relationship, okay, because my deformation is also linear. I know my stress is also linear because Hooke's law is linear, okay? And so here I have, bam, some stress, some shear stress on this increment area, some arbitrary radial distance rho away. So here I'll call that tau. And I know that the two, I can relate the two by similar triangles. This relationship would be tau max over c is equal to the shear stress at any arbitrary location divided by the radial distance to that location from the center. And it doesn't matter which line on the cross section I look at. So even if I were looking at some arbitrary line at this angle right here, my stress profile, my shear stress profile is the same, right? Because it's also, again, no matter what line I'm looking at, I have a linear distribution or linear deformation going from the center out towards the outer radius. And I'm going to experience here, we'll call this tau max, and then as well, like this. And it doesn't matter what line I'm going to have. If this is some location right here, and this is my distance rho as well, this would be, again, an arbitrary distance rho away from my center right here, intermediate, if you will, acting on this dA, my incremental area here. And we know that the resultant of all the shear stresses that if you will, the resultant of the shear stresses applied over this area, the torque that we sum up here has to be equal to that internal applied torque that internal torque that exists at this cross section. So what that means is that the torque, this internal torque, has to be equal to the sum of all the shear stresses dA times rho, because we have, this is a torque, right? Force times it. So tau times dA is going to give us a force, and then we need an arm or a distance, so we'll have this rho. And then this dA, just to make sure, is really a double integral in maybe like polar coordinates or something that you would have to resolve if you want to calculate this without the help of some other things that we're going to have. But here, for instance, let's substitute now this definition of the shear stress, tau, which is tau is equal to rho times tau max divided by c. And if I substitute that for tau over here, then I would get that the torque is equal to, let's see, I'll group the rows together. So I'll say tau max over c times rho squared dA. And in this case, tau max is a specific value at the very end, or at the outer radius or outer edge of my shaft. And c is also the outer edge. It's just the radius. These are all constants. And so this becomes this tau max over c is rho squared dA. And this right here probably looks like a moment of inertia, yeah, from statics. Anyway, right here, this is also the polar moment of inertia, because this right here, we're talking about circular sections and radial and polar coordinates. So this is our polar moment of inertia, which is defined as the resistance to twisting of my cross-sectional area, the resistance to twist. Okay, just like a moment of inertia, area moment of inertia was a resistance to bending. This polar moment of inertia is a resistance to twisting. And the larger my polar moment of inertia, the harder it is to twist something. And so this ends up in our very popular result, T, and the symbol used for this is J right here. So this ends up with our T max over C times J, the polar moment of inertia. And here, this is often rearranged so that the maximum shear stress in a circular shaft with an internal torque T is equal to times the radius divided by the polar moment of inertia. So this is specifically for the maximum. And at any other location, tau, the shear stress at some location rho, a radial distance away from the center, divided by the polar moment of inertia gives us our shear stress. And this is the shear stress due to torsion, or an internal torque. Okay. I have one word left for you. Done. Or in the famous words, I guess I have more than one word. In the famous words of our former California governor, I'll be back. Later.